Section 7.3 Sampling distribution of the sample mean. Sampling distribution. Before we talked about the variable x, how the variable x was distributed. Was it normal distributed or not normal distributed? Like it was symmetric bell curve, that's called normal distributed. So if someone like takes pick a large data and then they draw histograms for that data. This shows a histogram of a sample means of 1,000 samples, because notice what happened. They talk about 1,000 samples, not like 2 or 3 or 4. So then they notice that the distribution here for the x bar, so that's what that's x bar for the sample mean, is almost normal distributed. So we're going to see in this section what happens as we change the values of n. If we pick n2 and 5 and 100, what's going to happen? And then what we're looking for is the distribution. Means we are looking to see if the distribution is going to be normal or not. Will the distribution be normal or not? That's what this is about, this section. But the distribution will be normal or not for which variable? So before we were doing x as a variable. Here we have x bar, the variable. So for the sample means. Okay, so let's see what we have. First thing is sampling distribution of the sample mean. Okay, for a normally distributed variable x. So suppose that the variable x is for the population is normally distributed. So it's given x is normally distributed. So what happened with the mean? So it has a mean of mu and the standard deviation small sigma. Then for the samples of size n, the variable x bar is also normal distributed and it has a mean of mu. So the mean here means mu sub x is mu. And the standard deviation is the standard deviation of the population divided by the square root of n from the previous section. Okay? They just basically recalled what we did in the previous section here. Now what we need to do here, we're going to look at these examples here, and then we don't have to calculate them. Let's assume they are given to us like so, and here what they give us, that's the mean for the first one. Do you see this here means mean is 100 and the standard deviation is given as 16. Okay, that's what the pairs or the given couple or pairs means here. So they give us for the first figure the mean is 100 and the standard deviation is 16. So those are for the sample mean. So this is mu sub x bar, standard deviation x bar. For the second one, mu sub x bar is 100 and this x bar is 8. For the next one is still 100 and this one is 4. Do you see they coming from here? So as the standard deviation decreases, the points or the distribution gets smaller and smaller. So they all look normally distributed, but the last one, it's more like let's say skinnier or something. But what happened here is this thing here gets smaller, right? Like it was 16, then 8, then 4. What affected that is the sample size. So notice how the sample size was 4, then 16. So the sample size increased. So the sample size here, n was 4, here n was 16, here probably n was 1. So as the sample size increases, then the distribution becomes, or the standard deviation gets smaller, right? It gets smaller, and then the spread here, we call it, decreases as the sample size increases, right? We know this from the previous section because this is the standard deviation of the population over square root of n. As this increases, this decreases, and that's why this became like kind of skinnier, as you can see this. And then in this case, what happened is less errors would happen here, or something like that. Now, what we are interested here to know, okay, so you said as we increase the sample size, the sampling distribution here actually tend to be more and more symmetrical, and it tends to be more normal distributed when we increase the sample size. Now, is there any theorem that guarantees to us that, you know, if n bigger than some number, then we can say that this is normally distributed, like really the distribution for the sample mean is normally distributed? Well, let's see. Before we get to that one, note here what happened. If the variable x, so the variable x means that's for the population. If the variable x is normally distributed, automatically the variable x bar automatically normally distributed. The question that we're going to ask here is, how about if x itself, the variable x for the population, is not normally distributed? What happens to the x bar? Does it still hold? Well, yes, it still holds provided n is so large. So this means so large. So large doesn't mean 1 or 2 or 3. So large, I'll tell you what so large is. Then with that thing in mind, and a theorem here that researchers consider this as the most important theorem in statistics, which says for a relatively large size, sample size, means n, it's always bigger than or equal to 30. Keep that in mind. The variable x bar is approximately normally distributed, regardless of the distribution of the variable x itself. Okay, and so the approximate becomes better with increased size. So it becomes better and better as we increase the size or the sample size. This is important, very important. So n must be bigger than or equal to 30. So researchers agreed, okay, 30 or more, that's called a really large sample size from 30 on. And if we look at this data here, this I don't have the actual data here written on the screen, but they had a number of people they questioned. As you can see, when they found out, you know, they talk about, let's say, the frequency of something. So they found one person has, you know, that relative frequency, which came from the frequency, was maybe 0.23 or something. And 2 people had this frequency, 3 people next one, all the way to 7 people. So that's the number of people. So in total they had 7, 1 plus 2 plus 3 plus 4 plus 5 plus 7 plus 6 plus 7. So that's definitely more than 30, right? Is it either 30 or more? So you can add them up if you like. This is 13, 18, 22, 25, almost 30 people. Let me see. Again, 13, 18, 22, 25, 28. So not 30 as I expected this to be. But we can look at this distribution that they have here. What happened here? Well, we know if you look at the graph, this thing, it's mostly skewed to the right, as you can see, right? It's skewed to the right. Now, we tried to calculate the number of people here, but the size was not enough. And that's why the histogram tends to be more of skewed to the right. If we try to pick or select a sample size more than 30, so then the sampling distribution of the sample mean can be approximated by the normally distributed when the n bigger than or equal to 30. So by the central limit theorem, this guarantees that x bar is approximately normally distributed. So that would be more than 30. So here the sample size n was 28. But if I take like more, like let's say 5 more people or 10 more people or 20 more, then this histogram will tend to become more and more symmetric, like more normally distributed. That's what this is about. Now again, if you look at this one, imagine you have 1,000 samples of 30 household size each. So when you do it this way and you plot, you know, at least one of them, you will see how the difference between this histogram and this histogram. This second histogram looks more normally distributed, as you can see, because of the sample size, and that confirms the central limit theorem. So in summary, what we have, these quick facts, good to know. Suppose that the variable x of a population, so it's important to know what each letter means. So x is for population. we know has a mean mu and standard deviation this sigma. Then for samples of size n, the mean of x bar equals the population mean. So that's one thing. And the standard deviation for the sample means is this. If x is normally distributed, so automatically x bar regardless of the sample size. But if the sample size is so large enough means n bigger than or equal to 30, automatically x bar is normally distributed regardless of the distribution of x. If x is normally distributed or not. So if the actual population is normally distributed or not, this will guarantee this. Central limit theorem will guarantee this. Now, one other thing good to know to look at here, sampling distribution of the sample mean for different cases. This one is for the population first, and that's why you see x's here. So the distribution of the variable, what happened is it could go like the first one here, or the next one there, or this one. So the first one is normal distributed, and the second one is reverse J-shaped, okay, reverse G-shaped, and the last one is uniform. So what happened when I pick a sample, I sample the population from there. So I got this from there with size 2. I take 2 as we paired them in the previous 2 sections. Then for the mean, sampling mean, it will look normal distributed like this, which better than the one above it a little bit. And then this one becomes this one becomes like that. Now what about as we increase the size of the sample? So instead of 2, I'm increase it to 10. So to 10, then this one becomes like that, this becomes this. Notice how all of them now, they look more normal distributed. And now for n equals 30, and why they chose 30, because as I said, the central limit theorem should work with 30 or more. Then notice how they all look almost the same. That's how it shows us how the central limit theorem is really powerful. As long as you know the sample size, you can prove or you can state that the sample mean will have a normal distributed, will be normal distributed, even if the population is not normal distributed, or the variable x of the population is not normal distributed, still x bar considered normal distributed by the central limit theorem. So as n increases more and more, that's what it's saying. As n is sufficiently large, then x bar is normal distributed.